Okay, in this section, I'm going to be doing a couple of examples for you, and I will be following, as best as I can, the recommended method of problem solving as outlined in your book. They go into a lot of details. I strongly suggest you follow this procedure because it will prevent you from making very many mistakes. Most importantly is your setup. Prepare, draw your picture, define your coordinate system in symbols. When needed, draw a motion diagram or make a graph. Make an organized list of known values. Also identify what it is you're looking for. Do some preliminary calculations like unit conversions. Second most important thing is to solve the problem. Use some whatever equations apply based on your known values and what it is you're looking for. And if you can, be efficient with it, but you don't necessarily have to. As long as you get the right answer, that's all that really matters. There are many ways to solve these problems. Lastly, always think about your answer in lab as well and on your homeworks. Did you find what you were looking for? Right? Go back and check this. Is my answer physically reasonable? Are my units correct? This is the number one thing you can do to check your answer. All right, without further ado, this was my practice run, remove all annotations. Okay, and start again. We've got a rocket launching straight up with a constant acceleration of 18 meters per second squared. I'm going to go ahead and mark some important pieces of information. I'm going straight up. After 150 seconds, that's some time. Here I have some acceleration, in the y direction. I want you to be careful about your x and y. Now, even though we're only doing one dimension, because soon we will be doing things in 2 dimensions. 150 seconds is a time interval. How fast, something that I'm looking for, is the rocket moving, and how far has it traveled? Okay, so I can draw my motion diagram. Here's a y equal to 0, and also maybe an initial time. Okay, and our rocket is taking off. So it's going faster and faster and faster, and so on. We can also draw the acceleration. The acceleration always points in the direction of increasing velocity vectors, in this case in the positive y direction. Okay, let's make our table of knowns. We have the acceleration. Just one quick adjustment. So the acceleration in the y direction, going back to the problem, is 18 meters per second squared. My time interval is 150 seconds. What else do I know? Well, I'm looking for my final velocity, but I know something about the initial velocity. In fact, how fast is it going before it launches? Well, hopefully it's starting from rest. Then I'm looking for my final velocity. And I also want to know how far it travels. What is the final y position? Well, if we define the initial y position as 0. Okay, so let's take a look at the notes, make sure I'm doing this quickly and efficiently. So I'm going to use the kinematics equation, v sub y final equals v sub y initial plus a sub y times delta t. My initial velocity is 0, so that goes away. I'm already solved for what I'm looking for. The acceleration is 18 meters per second squared, times my time interval is 150 seconds. I can plug that into my calculator and I get 2,700. Check my units. Seconds cancels with one of those seconds, and I get a meters per second. So that's good because those units work out for velocity. How fast is that approximately? Well, let's convert it into something with which I am familiar. It's over 6,000 miles per hour. Does that sound about right for a rocket flying for, is that 2.5, 3 minutes? Yeah, sure, why not? I think a rocket could go that fast. Okay, I also want to know how far it's traveled, so I'm going to need some more room. Let's go to the next page. And I'm going to use this kinematics equation, y final is equal to y initial plus v sub y initial delta t plus 1/2 a sub y delta t quantity squared. Okay, so I've already defined my initial position as 0 and my initial velocity. I started from rest, so that's also 0. And now this simplifies very nicely to just one term. Okay, so I can now actually plug in numbers. Again, I'm looking for the y final. Everything is done. 1/2, my acceleration is 18 meters per second squared times a time of 150 seconds, and I'm going to square that too. Okay, plug that into my calculator. What do I get? I see this is 202,500 meters. Can round that to a certain number of decimal or significant figures, but I don't really care that much. It's about 202 kilometers. 200 kilometers? Yeah, that seems about reasonable for a rocket going into outer space. That definitely gets us quite far away from the Earth. Okay, good. Any questions? Let's talk about it in class next time we meet. And instead, let's go on to the next problem. Okay, this one, a fully loaded Boeing 747 with all engines at full thrust accelerates at 2.6 meters per second squared. Again, I've got some interesting things. We have an acceleration. Its minimum takeoff speed is 70 meters per second. I don't know yet if that's an initial or final speed. How much time, okay, I'm going to look for a time, will the plane take to reach its final takeoff speed? Okay, so this takeoff speed is the final speed. I'm going to make a note to myself. That's V final. Is that X or Y? Well, it's an airplane. Airplanes move in the X direction. And I also want to know the minimum length of a runway. So I want to know the displacement delta X or the X final. So let's draw a motion diagram, right? So my fully loaded Boeing 747 starts at an initial position of X equals 0. My initial time, 0, right? And I start with a small speed, and I get faster and faster and faster. Oops, I got one away. And so on. My acceleration, once again, is in the positive direction, in this case, horizontal, X direction. And that looks pretty good. So let's make a table of known values. Going back to the problem, I have an acceleration, a sub x equal 2.6 meters per second squared, significantly less than a rocket. Is that surprising? Not so much. The takeoff speed is 70. That is a final x velocity, 70 meters per second. Which means while I'm thinking about it, I'm going to put my initial x velocity, 0, started from rest. And what else do I know? Nothing else am I given, but I want to know the time interval that it takes to reach the final speed and also how far my plane went. Or I can either find delta x or I can find x final. I'm going to look for x final. Okay, so first things first, I'm going to find the time interval. And to do that, I'm going to use this expression. V sub x final is equal to V sub x initial plus A sub x delta t. Now, I want to find my initial time, which means I need to solve this for time. Now, you can plug in numbers first, but the only numbers I like to plug in are the ones that are equal to 0, because that simplifies my algebra. And I find that if I plug in numbers other than 0 and then solve, I always make mistakes. This way, I'm not going to make mistakes. So, looking for delta t, I only have these two terms, right? Vx final and a sub x delta t. So I'm going to divide both sides by acceleration. And I see that delta t is equal to v sub x final over a sub x. Now we can simply plug in numbers. How easy was that? 70 meters per second divided by 2.6 meters per second squared. If I put that into my calculator, that equals 27. And what are my units? Well, the meters cancel with meters. One of these seconds cancels with one of those, or the one on top cancels with the one down there. And then I'm left with seconds in the denominator of the denominator, which moves it to the numerator. And it takes my airplane about half a minute to go down the runway. That seems reasonable to me. Let's do part B. How long is the runway? Well, I'm going to use this expression here. X final is equal to X initial plus Vx initial delta t plus 1/2 plus a sub x delta t squared. I'm looking for how long my runway is. I've defined the initial position of the runway or the airplane 0. My initial velocity was 0, and now I'm left with this much simpler problem. So I can plug in numbers. This is equal to 1/2. Acceleration, once again, is 2.6 meters per second squared times the time interval of 27 seconds. That's what I found just above. So messy. Plug in these values, and I see this is about 948 meters. How far is that? Is this reasonable? Well, if I can convert that to miles, that's about 0.6 miles. Yeah, that seems about right. Runway, if I look at it, yeah, it seems about 1/2 mile long. Okay. Now you might be asking, well, I used the time that I found in the first part. What if I had made a mistake then? How do I know? Well, we can use a different expression to find how long the runway is. To do that, so this is a good way of checking your work. I can use this expression, I forgot my subscript, X final squared is equal to Vx initial squared plus 2a x final minus x initial. Now, this is a very powerful one. Notice there's no time in this equation at all. So I know that only things that were given to me in the problem I'm going to end up using. This term, the initial is 0. My initial x position is 0, and this simplifies to 2a sub x final is equal to v sub x final squared. So let's solve for my final position. That's what I'm looking for. So I divide both sides by 2ax. And I see that x final is equal to vx final squared over 2ax. Plug in numbers. My final velocity was 70 meters per second. Don't forget to square it. Divided by 2 times the acceleration, which is given as 2.5, is that right? 2.5? 2.6. 2.6 meters per second squared. So there's a typo in my notes, which means there might be a typo in my answer. So double check this for yourself. Put in a 6 there. That's really ugly. Right? Use the tools that you're given, right? Use the tools you're given. 2.6 meters per second. When I plugged these into my calculator, I got 980, but I might have plugged in 2.5 instead of 2.6, and I'm not going to check it right now, but you can double check that. In any case, it's pretty close to what I got above. Made me think, well, I might have had some rounding errors when I calculated 27 seconds, but they're pretty close to 1 sig fig. Yeah, so probably I plugged in the wrong number. Going back, I can check that. Now let's double check our units. So let's do a unit check. In the numerator, I have meters per second, but I'm squaring that. So meters squared over seconds squared. In the denominator, I have meters per second squared. So if it's in the denominator, then I can flip that fraction and put it in the numerator. The seconds all cancel, the meters mostly cancel, and I'm just left with meters. So that works out quite nicely. Okay. So these are a couple of examples. We will do some more in class together, and I'm going to make you do some more. But now I'm going to do the very last section.